Welcome. In this video I would like to demonstrate how to perform simple pyrolysis modeling with FireSciPy. As an example, I will be focusing here on a single-step pyrolysis reaction. First of all, FireSciPy needs to be installed. This can easily be accomplished using pip. The notebook that I'm using as an example here is also available from the Git repository. It is available from the path docs, tutorials, pyrolysis, notebooks, and then FireSciPy the KAS demo notebook. At the first step, here different packages are imported. This next cell contains some general information for plotting. This next cell provides an overview over the package versions that have been used for the computation. I've set it up here so that when you run the notebook, you get an overview over the package versions that are installed in your Python environment. This information will be provided in the output cell right below. You can compare this output with the package versions that I have been using. These are provided here at the top of the cell as a comment. This will also allow you to set up your own virtual Python environment using the same packages that I used. It is not strictly necessary to use these specific package versions. FireSciPy should also work with different versions, but in case you run into problems, this may be a way to solve it. During the creation of this notebook, I have used FireSciPy version 0.0.5, which is a development version. In your case, you will likely start with a higher version, presumably 0.1 and higher. Don't worry about this, it should all work the same. Now let's have a look at the single-step pyrolysis reaction modeling. This section starts out with some theoretical background, but I will not go into too much detail here. You will realize that when you go to the documentation webpage, the same information is provided there in the tutorial section as is used in this notebook. The first entry in the pyrolysis tutorials is the single-step modeling. And you can see here it is the same information. This means if you want to try out FireSciPy for yourself, you do not need to copy over all the Python code that is presented here. You can simply go to the Git repository and download the Jupyter notebook. The goal here is to model the conversion rate, d alpha over dt. This is expressed by a reaction rate constant, K, which depends on the temperature, a reaction model, the f of alpha, and a pressure dependence. In this case here we are neglecting the pressure dependence. Here we are using the common approach to express a rate constant with an Arrhenius equation. This means we are left with three parameters that can be adjusted. The first would be the capital A, the pre-exponential factor. Then we have the capital E for the activation energy, and the f of alpha as the reaction model. These three together are what is referred to as the kinetic triplet. If you're interested in more details on this, I strongly recommend that you have a look at the ICTAC recommendations. I've provided a couple of links here to these recommendations. I will also put them into the video description. Now let's have a look at modeling a single-step pyrolysis reaction. For this example, I've chosen a linear heating rate, beta, of 5 Kelvin per minute. The values for the kinetic triplet have been taken from the article that I've linked here. FireSciPy expects the pre-exponential factor in the units of 1 per second. The activation energy is to be provided in joule per mole. I've also provided here an alpha 0 value, which is basically 0 but not quite. This is meant to prevent numerical instabilities. FireSciPy also expects temperatures to be in Kelvin. So for our temperature program here, the starting temperature has been chosen to be 300 Kelvin and the end temperature would be 750 Kelvin. For the heating rates, FireSciPy expects values in Kelvin per second, but you can also provide Kelvin per minute. FireSciPy will internally convert the numbers. Furthermore, I've also defined some spacing for the temperature values, which is the recording frequency for our virtual TGA device. In line number 3, the number of data points is computed for the desired recording frequency for our virtual TGA device. Lines number 6 and 7 provide the start and the end temperatures in Kelvin. In line 11, I have defined the linear heating rate. Now, how do we generate the linear temperature program? From FireSciPy, we can now call the function create linear temperature program, which is located in the subpackages pyrolysis and then modeling. It takes as parameters the start temperature, the end temperature, the numeric value for the heating rate, the unit for the heating rate, again either Kelvin per minute or Kelvin per second, and the number of data points that is associated with the recording frequency. The results are stored in the variable temp program. In the next cell I'm separating the time and the temperature values from the data series that was generated by the function before. They are now used in the function solve kinetics to compute the conversion. Solve kinetics takes now the parameters the time series and the temperature series, the pre-exponential factor A that we have defined above, as well as the activation energy E. There's a value provided for the alpha 0 as well as the gas constant. In line 14 we can now choose a reaction model. In this case I've chosen the nth order model. Line number 15 allows us to provide a parameter that is associated with the reaction model. In this case here the n, which is set to 1, meaning that is a first order reaction model. For now there's only a limited number of reaction models available. For example, the nth order model, the power law, the Avami model, or the Sestak-Berggren model. This function provides two results, the time as well as the conversion. The available reaction models are sufficient to capture the main classes of reaction behavior. These are the accelerating, sigmoidal, and decelerating behavior. And the nth order model would be an example for a decelerating reaction. You can get this information by conducting isothermal TGA experiments. Then compute the conversion and plot it against time. In the next cell I'm simply plotting the conversion against the temperature. As a label I've chosen the heating rate beta. And here in this plot we can see the result of the conversion against the sample temperature. In the next video I will be demonstrating the Kissinger-Akira-Sondos method. It is used to compute the activation energy, for example from TGA experiments. And in this example I will be using the modeling capabilities I just demonstrated to create simulated TGA results. See you in the next video, thank you very much and have a nice day.